Hello everyone, welcome to the short webinar series on post-tension pre-stress concrete PSC bridge design as per Eurocode. We are going to create this bridge in Midas Civil software. Let me introduce myself first. My name is Nivedita Kumar. I'm the technical support engineer at Midas IT. The webinar series started yesterday, that is on 27th July, same time, and we had seen how to create a PSC bridge using a grillage modeling feature. Here we saw two ways in which we can create the model. One way was with the help of node and elements, and the other was with the help of wizard. Today we are having session 2, which is on loading and boundary condition definition. So we already have our model, and on that model, we will further go ahead and apply the boundary conditions and the loads that have been specified. Just like over here, we can see there is pre-stress tracking force. We will see tendon definitions and then static load definitions, moving load application as per Eurocode. We will also apply wind loads, and we will see how response spectrum analysis can be performed. Further, I would like to briefly describe about the soil structure interaction that can take place in Midas Civil. So that is about today, and tomorrow is the last day of our short webinar series where we will see the analysis results and how to extract them and generate high quality optimized design reports. So those would include the auto load combinations, the design, and also we will take out the results in the table format and generate a comprehensive analysis and design report using Microsoft Word, which is, by the way, inbuilt in Midas Civil. All right, so without any further delay, let us move ahead now to the contents of today's session. As I've already mentioned, we are going to look at how to create tendons and how to apply the pre-stress tracking force. And then we will see what all static loads would be applicable. After that, we will see how to apply the moving loads on the PSC bridge that we have already modeled. Then we will apply certain wind loads. I'll show the calculations, and then we will move to the dynamic response spectrum load application. And after that, we'll have a description on soil structure interaction. We will summarize today's session, and you can also write up your question answers. All right, so let us now go ahead and start with the boundary conditions of our software of our PSC bridge. Then we will move to the load application. So we will go now to Midas Civil software. Yesterday, we saw that using the wizard, we were able to apply the boundary conditions and the loads very easily. Just in the wizard itself, a lot of basic loads were applied. So I'd like to open that file right now and show what all things were already done by the wizard. So this is the wizard model. When we click on this hidden button, we will be able to see the actual line elements that the wizard has generated, the nodes as well. So here, let us go to the tree menu and understand the support conditions that the program already assigned. So this is a fixed support condition. We can right click in the tree menu and display it. Here we have some elastic links first of all, and below the elastic links there is fixed support condition. We can zoom in a little bit and understand that there are two nodes over here, and those two nodes are linked with this elastic link that simulate the stiffness of the bearings. So the actual stiffness and the shear stiffness of the bearings are simulated here with the help of the elastic links. Furthermore, there are certain beam end releases that have been assigned at the middle location, which are actually not used because we have made this two-span bridge as a simply supported bridge. So these will not be used as such. Coming to the rigid links, let's display the rigid links. So rigid links are necessary because we have generated a practical model where the section properties have got a section offset as center top. So to connect the top of our girder with the bottom of the girder and then to the bearings, we have to use a rigid link. So this rigid link is highly stiff and would transfer all the forces and the moments from the top node to the bottom node. And thereafter, there will be some bearing, and below those bearings, there will be fixed support condition. So this is the support that we are going to see how to apply on our manual model. So here is the manual model which we had generated using nodes and elements. Now we will go to the boundary tab and we will start with the defined supports. Now, when it comes to a PSC bridge, we would require to have construction sequence. The construction sequence information will be mentioned in the next session, but for construction stages, we need to use groups, and therefore we will go ahead generate some groups. So these are certain groups: substructure, rigid link, then girder elastic link, girder rigid links. These are certain groups that have been already generated. I will make use of these groups and apply my support conditions. So as we can see right now, there are no supports. We can understand that information from the tree menu itself. So that's a good thing to review the model. And let us fix all the support conditions with the help of substructure support group. We will apply this support condition at the bottom nodes of the start, at the bottom node of the pier, and at the bottom node of the end of the bridge. And then we'll click on apply. After this, let's go ahead to the next part, that is the elastic link. The elastic links, the general type of elastic links, shall be used for application of bearing data. So we need to specify the axial stiffness with the help of SDX and shear stiffness with the help of SDY and SDZ. So there is a local axis of our elastic link, and elastic link is also like an element. So if in case you want to know the forces inside the elastic link, you can generate them using Midas civil result tables. You can also provide stiffness for moments, and if it's like we have simulated this to be simply supported, you can actually avoid having any stiffness over here, or a nominal stiffness of 1 kilonewton meter per radian. Okay, so let's give a really high stiffness over here. I'm giving 300,000 as the vertical stiffness because we are going to model it straight way up. And there will be certain stiffness. I'm giving 3,000 and 3,000 for the transverse directions. And here I'll provide just one value for the X, for the moment, for the rotational stiffness. All right, I'll use this copy feature over here and I'll go for this Y direction and start providing the information like 4 at the rate 3 meters distance apart. And then I'll go ahead, click on one node and the second node. So this link that I have generated right now is copied to all the nodes that are spaced at 3 meters apart 4 times. Same thing, I'll do it over here. And that's in this way. And lastly, over here. So we are done with the bearing information. Now let's move to the rigid link data. So the rigid link data we will keep as rigid body, and we will provide information as substructure rigid link. This will be girder rigid link. Substructure rigid link will be there to connect the bottom of the bearings of the two spans and the center of the pier cap. So let us go ahead now and provide the information about our rigid links. Now, rigid links are generated with the help of a master node, which is usually at the top. So we have this as the master node right over here, and we will copy this rigid link in the Y direction, same as we did before. That is 4 at the rate 3 times. This top node of the bearing is going to be our slave node. We'll click on apply, and that is it. So this is what we're going to do over here as well. So here, let's move ahead and provide the information of the master node, and then we will select the top node as the rigid link. Okay, not this node. Okay, so it will be just the next node over here. So just to understand from the top view, this will be our master node, and this will be our slave node, and apply. So same thing, we'll do it over here. Select the slave node and apply. And lastly, at the end, slave node. This is our master node, and apply. So we are done with the application of rigid links for the girder. Now let's apply the rigid links for our substructure. So we will select the group, and this time we will have this central node as the master node, and the top, sorry, not the top, the bottom of our pairings will be the slave node. So this is what we have done right now. All right, so we are done with the application of boundary conditions. Now let's move ahead to the next part of our discussion, that is the moving load, that is the loads. So I'll just open my presentation. We are going to start with the pre-stress jacking stress definition. That means we are going to apply post tension with the help of tendons. So the jacking tension force is the force that is applied while we are applying the force on site itself. So it is without the losses. The losses will be automatically calculated by the program. The immediate and the long-term losses will be automatically calculated by the program. And that information for calculating the losses, we have to firstly start with the tendon property, and then we apply the tendon profile information using the tendon properties, and after that we tell the program how much of pre-stress is to be assigned, the jacking stress is to be assigned for each of the tendon. And usually, as per most of the standards, it is 0.7 to 0.75%, 75 of the ultimate strength provided in the properties of the tendon. So it's a three-step procedure, and let's go ahead and apply the tendon. So let's go to the load tab, then go to temperature pre-stress, and we'll start with the first tendon property definition. Here we have the tenant property definition. We click on add, and then we provide a name to it. We provide information about internal post-tension data. We have pre-tension and external tendon application too. After that, we will select the material for the modulus of elasticity for our tendons. And then the total tendon area can be calculated by the program using this tendon area calculator. So all you have to do is like select the strand diameter, provide the number of strands, and that is it. After that, we can provide the duct diameter over here, and then the relaxation coefficient can be selected from European standard with low relaxation coefficient. The ultimate strength can be provided, yield strength can be provided, then the friction loss will be also calculated based on the mu factor and the wobble friction factor. After that, we can have the anchorage slip loss as well, which is specified over here as 6 mm. The tenant property is going to be considered as bonded, and we can tell the program when the bonding is going to happen. So although for a given period of time, the tendon is not bonded, and then after grouting it becomes bonded, we have to provide over here bonded, and later on we can specify when it is grouted and then it will get bonded. Okay, so first step is completed. Now the second step. The second step is the tenant profile. Now there are ways in which we can create tenant profile. So here I have mentioned in my presentation, there is option to generate tenant profile with the help of coordinates. You can copy paste the coordinates from Excel sheet, Second method is with the help of tenant template. There is a tenant template option in the program. Then you can also import a tenant profile from AutoCAD, and you also have an option to create a text file and run it to apply the tenant profile. So if in case there are any modifications to be made, then there are options like the MCT file could be very useful and very easy to modify the tenant profile. So let's go ahead and see how to create the tenant profile. This is the most crude way, that is with the help of coordinates. Here you just specify the tenant name, which group it belongs to, and what is the tenant property, what are the assigned elements. Now to assign the elements, let us activate the girders. So we will select the girders with the help of section properties. So here we have some section properties, just select them, right click and say active. We can put them under the girder group so that it is easy for us to select and also to put them under certain construction sequence. So yes, we have our girders over here. Let us do the selection of our elements. We will apply the tenant profile to one, and then we can copy the tenant profile to the rest of the girders. So here we have options like different inputting options, and then we provide the X, Y, and XZ information in the plan. So I'm going to start with the 0. Firstly, it will be straight from the top view, like from the plan view. 23 also will be 0 from the center of the element. Then I'll go ahead provide the vertical information. So we start with at 11, we have minus 0.75. Then at 11.5, we have minus 1.338, and then we can fix it from the bottom. And then later on, we can go ahead with the last part and provide minus 0.75. So as you can see here, the program automatically makes it as a parabolic profile. And then we tell the program from where it should start, and that is it, apply. We have our tenant profile generated over here. So same thing can be done. We can have another tenant profile likewise, provide information over here like minus 1.15, then minus 1.6, and then minus 1.15 again. So I've created this information and I click on OK. So I can create a number of such tenant profiles. Now how to copy? Let's select these and say copy move, and then we can tell the program the equal distance. So equal distance is 0, 3, 0, because that's where our next girder will lie. And then we can click on OK. So this now new information has been applied to the next girders. Let's see that again. This is 0, 3, 0. Yes, so here we have these. Now we can copy the same at 0, 3, 0. Copy it. 0, 0. 6 was done. Now we'll go for 9. And let us copy it further at 12. So in this way, we have provided information for every girder. And further, all of these can be renamed and copied for the next span. So that can be done by simply selecting all of these and using copy move, and the distance now would be this will be 23.04 comma 0 comma 0. This is what we are going to do, and that is it. We have tenant profiles for both the spans now. We are done with the generation of the tenant profile. You saw how easily for so many girders we could assign the tenant profiles. The next step is to assign the pre-stress or the jacking stress. So we go to the third part, that is tenant pre-stress. And here we specify pre-stress information, firstly with the pre-stress load case, and then we provide information for the type, and we put it under the tenant pre-stress information. So firstly, we have T1 data, and then T2 data will provide all of the span pre-stressing together for now. And you can actually rename them and then accordingly put them one by one and assign them at different load groups and activate them at different stages. Even you can provide partial pre-stress at one duration, and remaining pre-stress can be applied at next duration. So that is also one procedure. Now let's go ahead and provide the stress. So the stress value is going to be 0.7 times the ultimate strength. So let us calculate that information over here. We will multiply this data by 0.7. So this is the 1300,000 is what we will take lump sum and provide that information right over here. 1300,000. So we can apply the stressing at the beginning only, or at the end only, or from both the locations. So to avoid the high friction losses, we can go ahead with both side jacking. So this is what we are going to specify. This is actually about the first jacking. You can put it at begin or you can put it at the end, so that that does not actually affect this information. This is where you tell the program if it is one side or or both the sides, or either of the begin or end. And then we can specify when the grouting is going to take place and click on add. That is it. So we are done with the application of pre-stress. Now let's move ahead to the next part, that is the dead loads. The dead loads would include self-weight, wet concrete load, because before the deck is cast, there will be some wet concrete load of the deck, which will act on our girders and diaphragm. So we will apply wet concrete load, and then there will be wearing course load, and there will be barrier load as well, and any additional component dead loads can be assigned. So let's go ahead now and apply these static loads. So we go here on the static loads and we start with static load cases, and we define information like the self-weight. This will come under the construction stage type of load case, because we are going to use them in construction sequence. So we will specify that, and then the wet concrete load will be again in the same, then wearing course, then we'll apply barrier load, and then we will go for additional components, but let's skip that for now. Okay, so let's go to the self-weight now, and in the self-weight we will select the self-weight load case name, and we will put it under the DC1, and make it, or the load group names would be very easy to understand if I just call them as dead load or self-weight, like that. So self-weight, modify, and then I'll make this as wet concrete load, and this will be my wearing course, and further this is going to be the barrier load. Okay, so that is it. Now let's move ahead and apply the scale factor for the self-weight. Then we will apply the element beam load for our barriers. So we will simply select uh, these nodes, or we can actually go ahead select the girder itself, and to these girder members we can apply. So like this, I'll select all these girder members. We can apply an eccentric load for the barriers. So we will go for the barrier load, and we will assign at an eccentricity from the offset, because we have put center top as the offset. And you can actually select global Y direction to make it easy for the application. So if we have 500 mm as the thickness of the barrier, then 1.5 minus 0.25 makes it 1.25. So at minus 1.25, I have the center of my barriers, and the load of that barrier I'm keeping as 10 kilonewton per meter. And then I'll click on apply. So that is it. Very easily we apply the barrier load. So same thing, we'll do it on the other side. This time we'll put it as a positive 1.25. We are done with the application of barrier loads. Now let's go to the wet concrete load. The wet concrete load will be a uniformly distributed load to all the girders, and this will be activated before the deck gets activated. So it will be the dead load of the deck, which would be 25 kilonewton per meter cube, and the density, and 0.25 is the thickness of our deck. Okay, and then we will uh, divide it into, or divide this particular area load into unit load along the girder length, and the girder center to center distance is 3 meters. So likewise, we can provide the information. Okay, so that is to be divided. So we will specify a value of minus 2.1 as the UDL for all our girders. So to select the girders, now we can make use of our toggle tree menu. You can double click on the girder to select them, and we will provide minus 2.1 wet concrete load, apply. That is it. Next is the wearing course load. Same thing we will do. We will be using 22 as the density of our wearing course, and 0.08 as the thickness of our wearing course or pavement, and we will divide it by 3. So that's 0.58. So let's provide this value, 0.58, to all our girders. So we will reselect the same girders, and we will assign wearing course load. That is it. So we are done over here with the application of all the static loads. Let's move ahead to the moving load definition now. In the moving load definition, as per Eurocode, we can have the vehicles as LM1 and LM3. The moving load application in Mitre Civil is very simple. It's a 3-step procedure: traffic lane, vehicles, and then there is load case definition. So let's go ahead and start with that. Moving load, we'll select first the Eurocode, then we'll define the traffic line lane. Let's create one lane right now, and this is how we have to specify the lane data. So if the lane is at the center, then of course it will be half of the width of our entire deck, that is 15 divided by 2. And if you have more number of lanes, likewise you should start from a particular reference line. So we will use one reference line, and we will go ahead and create these 3 lanes. So the first lane is at an eccentricity of 4 meters, and we'll keep the wheel spacing over here as 2 meters right now, and further you also have this option to do the transverse lane optimization with the allowable width of 3 meters. So these are certain additional options available. Cross beams, now you need cross beams, that is our transverse elements. So let's create some members in those cross beams. So live load cross beams are nothing but our transverse members. So for that, let us do the selection of only the elements spanning in the y direction. So let's hide and select in this way and use drag and drop feature to apply this particular structure group. And then we are back at the lane definition. So lane 1, and you can go ahead with the live load crossbeam. You can specify skew, moving directions. Right now we're specifying it in both the directions, and then the information about the reference line. So this is about creating the data. Okay, the live load crossbeams, sorry, we'll just avoid the diaphragms in it. So let's select the diaphragms and we will assign minus. So this is done. Let us define the moving lane again with 4-meter eccentricity cross beams, and we will define the reference line and apply. So this is our first lane. Then let us have the next lane, which is at 7.5. We will delete the table data, give the same reference line, click on apply, change the name and apply. Then the third lane, which is at 11 meters, we will delete this information, provide the reference line, and click on OK. So we have 3 lane definitions. Next step is to define the vehicle. And then we'll go ahead with add standard with LM1 vehicle definition. And we will also add LM3 with UK National Annex SV80. So this is what we will select right now. And then the third step is moving load case definition. We'll click on add here and provide the moving load case with the straddling effect. So here we can select all the 3 lanes. So these are the vehicles which would run on these selected lanes, and straddling will be done between these 2 and these 2 lanes. We can also create as a remaining area traffic line lane and put it under the remaining area list. That is it. We are done with the moving load case definition. Next, let's go to the wind load application. In the wind load application, we are considering the wind pressure to be applied on the bridge at 3 kilonewton per meter square. And we will calculate it with the help of section depth and barriers plus noise barrier, which total comes out to be 6.5. That's the information which we are going to provide. So the wind load is coming out to be a total of 19.5 in the horizontal direction, in this direction, and there will be some eccentric moment as well, which will be applicable at one single point. So we can provide this load, that is kilonewton per meter load, with the help of element beam load itself. So we will create one wind load case. This time we will use wind load on structure. So that will be the the type of load which will be used. We are selecting right now the wind load cases, or rather the cases that are selected over here are for automatic generation of load combinations. So let's use element beam load, use wind load from here. No need to select any group. We will not specify it um, into any construction stages as such. So let's provide 19 kilonewton, 19.5 kilonewton per meter, and we will apply it directly to these. So these are selected and apply. Oh, we need to take care of the direction. So we'll select them again and apply. Okay, so this is about application of the wind load. And you can also apply the uniform moving loads moments with this option. And this will be about global X direction. So the moment now is 28.47. So like this, we can go ahead, select the elements again and apply. So this is about application of moving load in as per any standard, actually, not just the Eurocode. Let's now go ahead and see how to apply response spectrum loads and in MIDAS Civil as per Eurocode. So MIDAS actually has a response spectrum analysis, pushover analysis, boundary nonlinear time history analysis, and inelastic time history analysis. So response spectrum is actually our linear dynamic analysis. Pushover is our non-linear static analysis. Then there is for dampers isolators, we have non-linear time history analysis where seismicity is taken into consideration and with the help of time history analysis. And you can also specify hinges, non-linear hinges, and perform a dynamic analysis. So non-linear dynamic analysis is also possible in the program. Okay, so let's go ahead to MIDAS Civil and see how to apply the response spectrum load. So we go to the dynamic loads, and it's a two-step procedure. We start with the response spectrum function, which has a design spectrum as per Eurocode. We select all the site-specific data and finish with the design spectrum. Then go to the RS load case and define the angle. So I'm going to apply this in the Y direction. So this is our Y direction. And for that, excitation angle is 90 degrees. And check on the design spectrum and add. That is it. If you want to apply it in the X direction, make it X. Make the excitation angle 0 and then add. And lastly, define the mode shapes that would be required. Now, in case of our bridge, Ritz vectors would be very much useful, wherein you can select the ground acceleration X and Y and have more number of mode shapes to get 90% of mass participation at lesser number of modes or quickly. So that is a Ritz vector. And that is it. So this is about application of response spectrum. Note that when we go ahead with modal analysis, we need masses. So in the program, we have this option to convert sulfate into masses. If you're applying loads in the X and Y only, then no need to go for Z, just X and Y is enough. We can also convert externally applied loads into masses. So that is right over here where you can convert your dead loads into masses. Like that. That is it. So this is about application of response spectrum load and also using the automatic conversion of loads into masses. Finally, let me talk about the soil structure interaction. In MIDAS Civil, you can simulate the pier cap, pile caps, and piles. And to those piles, you can apply pile springs by simply specifying the geotechnical data. So once you provide the information in MIDAS Civil about your depth and what are the soil conditions, if it's a clay soil, sandy soil, so likewise you can specify and the program will automatically assign the vertical linear springs and the non-linear horizontal springs to each and every node of the piles. So this is how you can apply or perform a soil structure interaction within MIDAS Civil. So this is not only applicable for pile springs, but if you have got integral bridge with abutments, then for those abutments as well, MIDAS Civil is capable of assigning the soil springs. So this is it regarding the soil structure interaction. Another part about soil structure interaction is that you can take your bridge into geotechnical software for making it a little bit more detailed and more accurate geotechnical analysis. So that is it from my side. Let us summarize today's session. So in MIDAS Civil today, we saw how to apply the boundary conditions and loads on a PSC bridge. There are all necessary load applications as per code provisions available in the software. You can apply moving loads very easily. No need to manually apply the moving loads using static loads and then create manually the envelopes and then take out the critical results, which is quite time consuming. So it's much easier in moving loads. Apart from that, there is optimization too. Another part is we saw today was about tenant profile, which was very easy to apply for different girders, and how various ways are available for us to define them. Then the application of wind load on bridges was very easily done by simply calculating the forces and applying using the element beam loads. There were gravity loads also, which we applied with the help of element beam loads. Then the response spectrum loads were available in Midas Civil for applying the linear dynamic seismic load on bridges. We also discussed about soil structure interaction that can be done for pile foundations. So that is it from my side. Thank you very much, everyone, for attending today's session on moving load analysis. On load and boundary conditions of PSC bridge. So hope to see you again tomorrow. Thank you very much. In case you have any questions, please write to me at nivita@midasit.com, or you can give, if you are the user, then you can send us queries on globalsupport.midasuser.com. And any question related to licenses, please send an email to Mr. Pankaj, and that's the email, pankaj@midasit.com. All right, there are some questions which I would really love to answer through email, and I would share those questions to all as well, so that everyone gets to know about some questions that are coming up, and that would be probably applicable to your bridges too. Yes, the session is recorded, and we shall send the recordings through emails itself to all our attendees. All right, so thank you very much again, everyone, for attending today's session. Please do share your ratings after the session is done. Okay, then that is it. Thank you very much. See you again tomorrow. Have a great day. Bye-bye.